All right. So let's go through the first few slides of this, see what we're discovering from this activity. So in the first few, in the green one, it talks about finding the area of the green rectangle. So if we check it out, it looks like lots of people have saying it's 32, which is good. How are you finding the area of this green rectangle? Length times width, right? We know this from even before we came here. We knew that the area is length times width. So if the length is 8 and the width is 4, 8 times 4 is 32. Now, next to it, it has the same idea, but it's written differently. What is 2 to the power of 3? Oh, thank you. What is 2 to the power of 3? Think of the exponent, 2 to the power of 3. So we go 2 times 2 times 2. 8. And what's 2 to the power of 2? 4. So the same idea, 8 is just written as 2 cubed. And 4 is written as 2 squared. And then when we multiply those, we know that the answer is 32. But it's written as 2 to the power of 5. Is that true? Go to your calculators. Grab your calculators. If you need a calculator, come get one. Are you getting a calculator? That's why I just said, come get one. Let's put our phones away. Okay. Everybody, phones in your pocket or your bag or someplace else, not on the desks. You got a calculator, good. Logan, you have a calculator? You need a special invitation, is that the idea? No. All right, on your calculator, 2 to the power of 5. So remember, you're looking for either this button or something that looks like that. So you're going to push 2 and then one of these buttons and 5 and equals. And what are we getting? 32. So it's saying that this representation is exactly the same as the green representation on the left. Okay. So if you follow this pattern, what do you think the area of the purple triangle is going to be? So here it was 2 to the power of 3 and 2 to the power of 2 ended up being 2 to the power of 5. Here it's not 2, it's a. A to the power of 3 times a to the power of 2. What do we think this is going to be? A to the power of 5? How'd you get that? Yeah, looks like the 3 and the 2 got added to get the 5. Let's see if that's right. Now remember how to push this into our calculator? So a to the power. How do I push the power button on Desmos?
It's that little hat.
Yep, and it's, where is it on your keyboard?
It's on the 6.
Yeah, so shift 6. And we put 5. A to the power of 5. Let's see if that's right. Oh, I know it's right. But Ashton told us that we added the exponents. All right, let's see if we can see any playing around with this. So let's see what you guys did on this. See what sort of rules people had. Orange will change the number, blue will change the exponent on the left, and purple on the right. Good. Good. Red equals the start at 5 for everything. The purple goes up. Okay, good. And we have all sorts of different ideas. Let's check what's going on here. So this, let's change the base to 3. Let's change the green exponent to 3. Or no, let's change this to 2. So it goes back to the one that we just had. And we'll change this to 2. So look at what we have up here. This is replicating what we had on the previous slide. Remember, 2 to the power of 3 times 2 to the power of 2 ended up being 2 to the power of 5. So 2 to the power of 3 times 2 to the power of 2 ended up being 2 to the power of 5. And what this is doing is showing you one of the reasons why. Does this rule hold true? So Ashton's told us that we're adding the exponents. What if I change this exponent to a 4? Does it still work? 2 to the power of 4, 2 to the power of 2 ended up being 2 to the power of 6. What if I change this to 4? Is the rule still working? 4 and 4 is 8. Change this to 5. 4 and 5 is 9. Doesn't matter what the base is. So I change this to base 3. Base changes, but the exponent's the same because we're still adding the exponents. Even if the base is a letter, that rule seems to always be applying about adding the exponents. Let's talk about what you're seeing up here a bit more. So what we're trying to do is multiply exponents here, multiply powers. So we've got 2 to the power of 3, and we're multiplying. You can use a little dot for multiplying, or you can put a times, the times thing. Two to the power of 2. What does 2 to the power of 3 mean again?
It's 2.
Okay, so 2 times 2 times 2. So this is 2 times 2 times 2. And what's 2 squared mean? 2 times 2. And what am I doing to do these two things? I'm multiplying it. So it's 2 times 2 times 2 times 2 times 2. What's another way to write this? 2 times 2 times 2 times 2 times 2. 2 to the power of 5. And that's what this is demonstrating. Here I got 3 and 3. There's 2 to the 2 times 2 times 2 times 2 times 2 times 2 ends up being 2 to the power of 6. If I change this to 5, you've got 2 times 2 times 2, but this would be 5 of them. And then if you're multiplying them together, you'd have a total of 8, which is what we have here. So this rule we can use on any of the bases. It says if we're multiplying powers with the same base, we can keep the base and add the exponents. So in the first example up here, a to the power of 7 times a to the power of 4. What am I going to do to the exponents? Add them. And so what do we think the answer is? For the red expression, if we're adding the exponents. A to the power of 11. So let's all get to slide 5. Red problem. You're taking the same base, you're multiplying them, so you're adding the exponents. So 7 and 4 is 11. What would the blue one be then? X to the power of 14. And try the green one. Doesn't matter if we have a negative. We're still going to add them. So -3, which is down here, kind of cold. Adding 8 is 5. So Ashton's telling me it's y to the power of 5. Let's check and see if we're right. There we are. What do people say for this one? We're on slide 6 now. Find things that, when multiplied together, is going to get you a to the power of 10. Your list might be in a different order than mine. Will this one get me a to the power of 10? If I add those exponents, will it get me a to the power of 10? Yeah. -2 plus 12 is 10. Is this one going to get me a 10? No. How about this one, Logan? Yep. This is an interesting one. Is there an exponent on x? Doesn't look like it. So if you don't see an exponent on x, it means x to the power of 1. You're not really multiplying it by anything. It's just x. So it's x to the power of 1. So if this is x to the power of 1 and this is x to the power of 9, do those exponents add up to 10? Yeah. So that one should work. Is this one going to get me a 10? 3 and 5? Nope. How about 2 and 5? Nope, that's going to be a 7. 2 and 8? Yeah. All right. The x to the power of 3 part and the x to the power of 4 part, we already know is going to get us x to the power of 5. But here I've got some coefficients. If I'm going to multiply the coefficients, what is 8 times 4? 32. So the coefficients are just plain old normal numbers that multiply. Okay, if this just said 8 and this just said 4, 8 times 4 is 32. But it's not 8 and 4, it's 8x cubed and 8x squared. So the coefficients still multiply together like normal numbers. And then when you multiply the exponents, you add, or when you're multiplying the powers, you add the exponents. So this should be 32x to the power of 5. And if I erase all my scribblings, we'll see that that's x to the power of 5. 32x to the power of 5. So let's try this one then. I'll give you a second, actually. Let's all go to slide 8. Hey.
Hey.
See you. Thanks.
You're welcome.
Grab a Chromebook.
Okay.
So the first part is 3 times 5. Those are just regular numbers. 3 times 5 is 15. These are powers. Do they have the same base? Yep. So what do I do to the exponents when I'm multiplying? So it'll be 15a to the power of 9. I'm going to just check that one. Looks like we've got that right. All right, so I'm going to move over to our notebook file here and hand this out. Okay, so you can just push the Chromebook off to the side, grab a pen. We're going to make this note. All right. So today we're doing exponents, but we're doing operations on exponents. Being able to get bigger operations on exponents. Tomorrow and Thursday, we're going to be doing volume and surface area. And there's going to be tons of exponents popping up when we're talking about volume and surface area. So that's why we're making sure we get these rules and tools to make that work easier. Think back to when we did algebra. We did collecting like terms, and rainbow was to make complicated expressions easier. The exponent rules do the same thing. Get complicated big numbers into something that's easier. So from our Desmos activity, we discovered that when we're multiplying powers with the same base, we keep the base and add the exponents. So the formal definition is written on your page there. B to the power of m, some base to a power of m, times another base, the same base, to a different exponent, is found by doing b to the m plus n. So on your top of your worksheet there, the algebraic description, you need to fill in b to the m plus n. This is just a mathematical rule that explains the thing we just discovered. When you're multiplying powers with the same base, you keep the base and add those exponents. So let's see a couple of examples of this. So the first one that we discovered when we were doing the Desmos activity was this idea. 2 to the power of 2 times 2 to the power of 3. If we write it out like we have over on the whiteboard here, 2 to the power of 2 means 2 times 2 times, oh wait, that's just 2 times 2. 2 to the power of 3 is 2 times 2 times 2. And we're multiplying those together. And so now this is a representation of 2 to the power of what? 5. We, of course, aren't going to be expected to write these out all the time. The rule tells us that we know that it's going to be 2 to the power of 5. This works for all bases, provided the bases are the same. It doesn't matter if the base is a number or a letter. So in this case, bless you, this is y to the power of 3. So that means y times y times y. Remember, y cubed means y times y times y 3 times. What does y to the power of 4 mean? Very nice. And I'm taking those two things and multiplying them together. And this can be expressed as a single power of y to the power of what? How many of them are there? 7. The rule tells us that we can go straight from here to here, here to here. If there's a coefficient, coefficients are just plain old numbers. They're not exponents. those multiply them normally. If I were to write this out, 7x squared would look like this. 7 times x times x. The 7's not being squared, only the x is being squared. It's just 7 times bigger. The 4x cubed is a 4 times an x times an x times an x. 4x cubed, only the x is being cubed, x times x times x. And then that answer is being multiplied by 4. These two things are being multiplied together. So I can simplify it by looking at the 7 times 4. Those are just plain old numbers. What's 7 times 4? 28. So this is equal to 28. But now I've got an x times an x times an x times an x times an x. How many of those do I have? 5. X to the power of 5. And again, I don't expect us to have to write this out all the time. We can go straight from here to here. That's especially valuable if we get really complicated stuff. So for example, what if we had 2x to the power of 20 times 3x to the power of 5? Do I want to write this out 20 times? No. Nor do I want to even write that one out 5 times. That's okay. I can still skip this and go straight to my answer. The 2 and the 3 are just coefficients. They're just numbers. So when I multiply 2 times 3, what do I get? Sorry? 6. But when I multiply the powers, what do I do to the exponents? Add them. So how many x's will I end up with? X to the power of 25. Oops. Okay. All right, so this is the first simplifying rule for exponents. Takes big, complicated exponents and makes them into a single, simpler exponent. Multiply the numbers, and then multiplying the powers means we add the exponents. Now, the second rule you would discover on here, but I think I'm going to go straight to it because I think you might have a guess of what this is. So when I multiply powers with the same base, I keep the base and add the exponents. Any guesses of what I do when I divide powers with the same base? I keep the base and do what to the exponents? Subtract them. It's written right up here. So it's not surprising that if division is the opposite rule for multiplication, right? They're inverse rules. Multiply, divide, they're kind of connected. They're inverse operations. So not surprisingly, if when I multiply, I add the exponents, here when I divide, I have to subtract the exponents. So the rule has us b to the m minus b to the n equals b to the m minus n. So make sure you put that to finish your algebraic description on the bottom. So how does this work? Well, what does 3 to the power of 5 look like if I expanded it out? 3 to the power of 5 means good. 3 times 3 times 3 times 3 times 3. Divided by, and then 3 squared is just 3 times 3, right? All right, grab your calculator for a second. I want you to try something. Pick any number, type it into the calculator. Doesn't matter how big it is, how small it is. Pick any number. Times it by 3. Now divide it by 3. What do you get?
It's
the same number back, right? Because if I multiply it by 3, that means get it 3 times bigger. And then if I immediately divide it by 3, get back right back to the same thing.
Is that the same if you were to like multiply and divide it by like 5 or something?
Sure. Yeah. Yeah. 5 times bigger, and then divided by 5 gets you right back to where you started. So what's happening here is I have all these numbers, but I'm timesing by 3 and then immediately dividing. Remember, this means divide by 3, and it's as if it wasn't even there. Can I do that more than once? Sure. Times 3, or divide by 3. Can I do it again? Well, no, I don't have any more dividing. So what am I left with? 3 times 3 times 3. 3 to the power of 3. And the division rule says I don't have to do this thing. I should be able to go straight from here to this. How? By subtracting the exponents. 5 minus 2 is 3. So let's predict what the answer for this one's going to be. I don't care that it's an x. X to the power of 2. Okay, we could write it out to prove that that's right. This is x to the power of 6. So that's x times x times x times x times x times x. Did I do that right? 1, 2, 3, 4, 5, 6. Yeah. Divided by x times x times x times x. Let's cancel. 1 will cancel with 1. Another one will cancel with another one. Another one will cancel with this one. This one will cancel with this one. Do I have any more to cancel out? What am I left with? X times x, which is x squared. So again, we don't want to write this expanded form out all the time, but we could. But when we get numbers really, really big, that's going to be a waste of time. We'll just use the rule. Yeah. Okay, great question. What operation is this asking me to do? Divide. Right. So let's just ignore this. What if I just had that? Oops. Yeah, and what's 20 divided by 4? Yeah. So the number, since you're dividing, you just divide normally. But this, that's not a number, that's a power, that's an exponent. So when you're dividing those, you have to subtract the exponents. So Ashton, what do you think the answer is going to be? 5x to the power of 2. I agree with what Ashton's saying. Let's expand it out and see if that works. This would be 20 times x times x times x times x. This would be 4 times x times x times x. The x's will cancel. 1, 2, 3 of those. I'm left with just, oops, I canceled the wrong thing. So there. Oh, I didn't have enough x's up top. So that'll cancel that, that'll cancel that, that'll cancel that. There we go. So as we suspected, all the x's will disappear and you're only left with 2 of them, which is x squared. And then the number is just 20 divided by 4, which is 5. And again, we don't want to write this out every single time. So I'd like to just use the rule regardless of how big the numbers are. So if I have 100 x to the power of 20 divided by 25 x to the power of 16, I don't want to have to write that out 20 times and 16 times. Let's skip that part and go straight to an answer. Are these exponents, the 20 and the 25? Are they exponents? No, they're just numbers. So what's 100 divided by 25? Yeah. And then these are the exponents? Yep. So what do I do to the powers? What do I do to the exponents? I'm dividing, so I'm going to subtract them. 20 minus 16 is 4. All right, let's go back to Desmos and see if you can use this idea in the next part of the activity. So now I'm going to try slide 10 to 15. Actually 18, sorry. All right, we're on slide 12 here. Same idea in that we're looking at the area of a rectangle, but this time I have the answer, and you need to figure out one of the sides. So if you know that the answer is 243, and one of the sides is 27, how would you figure out this side right here? Right, we got to use divide, which is this whole other part. So help me out here. What's 243 divided by 27? 9? Yeah, so remember when we do area, it's multiplying. So Milo, the opposite of multiplying is going to be to divide. So is it 9? So same idea here. If it's a to the power of 5 is the answer, and this is a to the power of 3, what must this be to make this work? A to the power of 2. So let's try that, a to the power of 2. And you can see that that splits up into 3 cubed and 3 squared, which is 9. And a to the power of 5 splits up into a to the power of 3 times a to the power of 2. So the same idea that we were just doing on our worksheet, if we chose, let's keep 2 as the base, and let's make this 5, and let's make this 2, then of course, 2 of these will cancel, 1 of them will cancel, 2 of them will cancel, and we'll be left with just 2 to the power of 3. If I change this to the power of 4, 5 minus 4 is 1. Does it matter if I change the base? The rule is still the same, but the base, of course, is going to change to 3 to the power of 1. If I made this just 2, 5 minus 2 is 3. It doesn't matter if the base is 2, 3, or a, the same idea is happening. So then just from what we did there, what's a to the power of 7 divided by a to the power of 4? A to the power of 3. This is written as division as a fraction, but still can be the same idea if you use the divide symbol. X to the power of 9 divided by x to the power of 5. What do I do to the exponents? Subtract, so it's x to the power of 4. And then the green one, y to the power of 5. Let's check and see how we did. A to the power of 3, a to the power of 4, a to the power of 5. Okay, and then it doesn't matter if we have that coefficient, it's still the same idea. We're just going to divide the coefficients. So help me out here. What's 18 divided by 6? Close. 3? And then a to the power of 7 divided by a to the power of 2. What do I do to the exponents?
5.
Subtract them, so it's not just 5. A to the power of 5.
Yeah.
Very nice. How about this one? 12 divided by 6? 2. X, and then what do I do to the exponents? So x to the power of 1. Now, you could either write x to the power of 1, or you can just write x, because we know that that means x to the power of 1. Good. All right, let's head up to the whiteboards.
That would be
Nice. Good. Okay. Very good. You do see now? Okay, look around, see if your answer matches other people. Okay. So I did this on purpose because I thought I might catch a few people. This is why the whiteboards are so valuable. We can catch this mistake now. This 12 and this 2, are they coefficients or are they part of the exponent? The 12 and the 2. Is that 12 part of the exponent? No. Is the 2 part of the exponent or the power? No. What do we call these? They're out front. We call them coefficients. Okay? So those we just behave normally. Now, in this one, is 2 a coefficient? There's no x, that's part of it. Yeah, that's right. But this is just a base in the exponent. This is 2 to the power of 5. So 2 is the base, not a coefficient. So when I'm multiplying powers with the same base, I keep the base and I add the exponents. So what's my answer to this one? 2 to the power of 7. You can see it right here. Everyone told me this was x to the power of 7. So if the base is 2, it's 2 to the power of 7. Okay, it's very tempting, I get, to try and multiply those numbers, but those aren't numbers, those are bases. So when they're bases, we keep the base and we add the exponents. So we all made that correction? Good. Okay, how about D? Good. Good. So in this case, of course, we're multiplying the exponents, or the powers, or the coefficients, excuse me. So that's 12. And then do you think the rule changes if I have a negative exponent? No. I'm still going to add them. -2 is kind of cold. Add 7, where am I? Yeah, x to the power of 5. Okay, good. Keep going. Okay. Looks like everyone got x to the power of 3 for this one. How'd you come up with 3? Subtract, good, because we're dividing now. These numbers here, 24 and 12, are those part of the exponent, the power? Right, so I just do what to those? Divide those, so that's what, 2? X to the power, and then I subtract those exponents. Good? All right, you can erase the board, come back down. Okay, we'll see you in 10.
I've never